Great. So what we are going to learn in this course is essentially, well, the name of the course is Thermodynamics, right? What does this, I mean, if I look at the simple English terms, thermodynamics, what does it mean? Thermo is heat. Yeah, that's what the idea is essentially. So that's heat. And dynamics is motion, related to motion, right? And now, why do I call it thermodynamics and not energy dynamics or something of that sort? That's historical. Heat was believed to be something that could flow. I don't know. I'm sure you've heard of these calorics and all these kind of stories. Heat was a fluid. In initial days, heat was supposed to be a fluid. It could flow from one place to the other. It's easier to think of heat flowing from one place to the other rather than thinking of cold flowing from one place to the other. Why? Yeah, people could light up matches, they could heat things up, they could light up a fire, they could see heat flowing, right? Refrigerators were invented much later. So it's essentially what we are going to study is the motion or the flow of heat, or in more broader terms, flow of energy. And we all know, keeping apart E is equal to mc square, keep that aside, then we all know that energy can neither be created nor destroyed. So that's the first law of thermodynamics, right? But it's very common sense law. You just can't create things out of nowhere. No? Well, Einstein was also very clever. Right? He was very intelligent. He said, look, I'm not going to disturb whatever has been established in thermodynamics. I know that mass can be converted into energy. But what was I going to say? I said, energy could be converted into mass. Have you studied anything about that? I was wondering the other way. The volume is low, or is it the acoustics?
We can increase the volume definitely.
Okay. So, E is equal to mc square, right? Mass can be converted into energy. Is the reverse true? Can energy be converted into mass? Yes? No? Or don't know? How many yeses? Oh, quite a few. Then we can have some examples too.
Speeding of sir, in the LHC in Geneva, there was an experiment or something that fast moving photons or something created mass.
Great.
Whenever we speed in matter and it represents mass.
Okay. Right. So these are not very common experiences, but there is a possibility. On the other hand, mass being converted to energy, that one is more easier to see, right? It's not about burning fossil fuels. You're not converting mass into energy, or are you? No. That's chemical energy, right? You're not destroying any mass. It's only in the nuclear reactions that you do convert some mass into energy. But yeah, the main idea is that even if you take that in the picture of thermodynamics, the laws of thermodynamics still remain valid. We also account for the interconvertibility of mass and energy. So it's essentially about the flow of energy, right? The exchange of energy between different systems, right? So if I'm going to talk of different systems, I'll have to make some definitions over there then. Okay. Before we go into definitions, so what I'm going to cover in this course are essentially 4 things. Right? The first one, which came later actually, is the Zeroth Law. Right, we have the 4 laws of thermodynamics, right? Zeroth Law, and that defines temperature. We'll come to these laws one by one. Then we have the first law, that's conservation of energy. Okay, let me change this notation right away. We will not use E but U for energy. Right? So it says everything is interchangeable. Energy can neither be created nor destroyed, but we can change it from one form to the other. The second law defines entropy, and it says that no, you cannot conserve energy. Right? But you conserve energy, that's not the fact. The problem is that you cannot completely convert one energy from one form to another energy to the other form without any losses. That's what it says. Right? It says yes, but you can do it provided you're working at 0 Kelvin. It defines entropy. We'll come to all these things. What exactly entropy is. And then we have the third law, which gives a numerical value to entropy, right? Numerical value of entropy. And it just tells you that, look, the second law has told you, yes, you can convert from one form to the other. The first law is valid at 0 Kelvin. The third law says, look, buddy, 0 Kelvin is not achievable. Right? That's what the third law says. It's all these laws are related to each other, and the way we'll go is in the same fashion, starting with the 0th law, then the first law, the second and the third law. But before we start, I'll give you some formal definitions, right? I'll just use some of these notes over here, which I have, and give you some of these definitions. What do we need to define first? First thing is, there is something called a system, right? And the system, so essentially when you're talking about thermodynamics, you're talking about the flow of energy. And if you wish to say that, okay, energy is conserved, you have to consider the entire universe, right? So system is that part of the universe which is of interest to you, right? So the first one is the system, and then the rest of it is called the surrounding. You know, so that's your system, and everything else is the surrounding. Fine, let me make this different color. Everything else is the surrounding. Let's say the rest of the board over here is your universe. So everything else is surrounding. I think you've already come across some of these trick questions where actually you see that the entropy of the system is decreasing, but still the process is spontaneous. Because the total entropy of the universe is actually increasing. Right? We'll again see some of those examples and try to rationalize them as well. The third thing that is very important out here is this fellow, which is the boundary. Okay. What happened? Ah, this fellow doesn't have red. No, I can't see any red. So let me use another color. I'll ask them if they can repair it. Okay. So whatever is not the system, that's the surrounding, and whatever separates the system from the surrounding is the boundary. Now, there could be various kinds of boundaries. For example, if I'm all these, whatever definitions you're given are very idealized definitions. Remember that. Okay? They're very, very ideal. And it's extremely impossible, almost completely impossible to find a real life situation which can very closely represent some of these idealized versions. So whenever I say this, for example, I say a diathermic boundary or a diathermic wall, right, is the one that allows heat to flow through without any losses. In reality, you can't find such a thing. Right? So, whenever we come to the real systems, whatever best approximations we can make, we will make. But at the back of your mind, always bear this in mind that these are all real systems. Whatever best mathematical equations we give, will never win. Huh? But just like a bunch of students around. Huh? So you could have a diathermic boundary, for example, which allows flow of heat. You could have adiabatic boundaries, right? You could have quite a few of these kind of different boundaries. The system could be open. Okay, there are 3 of these different definitions out here. The system could be an open system, right? Which means that it can exchange matter and energy with its surroundings, right? An example of an open system? Open beaker, right? Oh, we are an open system. Look, I'm sweating. I'm exchanging energy, I'm exchanging matter with the surroundings. Then there's a definition of a closed system. This fellow cannot exchange matter with the surroundings, but it can exchange energy. A closed system. And then finally we have an isolated system. And the isolated system, of course, cannot exchange either mass or energy. So these are the kind of systems that you'll be dealing with. Why can't I have a system that can exchange only mass and not energy? something for you to think about. Why I cannot have a system? I have told you this one can exchange mass and energy, only energy, nothing. There's another possibility, right?
Mass is a type of medium through which energy can also transfer.
Okay.
So, like if the temperature of the mass is higher, it will take the energy outside.
Great.
It will not have mass at zero. Magnetic intensity.
That's the answer, right? That's where the third law comes in. So these are the three kinds of systems that we could have, right? There are a few more things which we essentially want to know about the system. I'll not describe everything so formally, but as we go through the examples and so on and so forth, we'll know that some of these, in different circumstances, could be useful. If the system is homogeneous or heterogeneous, this will come after, let's say, about 10 lectures. We start with single component systems. Right? We develop all the laws, we develop the Maxwell relations for a single component system, and later on we come to solutions, mixtures, things. If the system is in an equilibrium state or not, this will be very useful. And these are things which you've already seen, right? You've seen some of the examples: A plus B in equilibrium with C plus D, right? How many components are there in this system? These are things which you really need to know. When you talk of the phase rule, for example, or the phase diagrams, you'll see there are various different components. For example, the phase diagram of water is it's not very simple, but whatever you'll learn is very simple. You'll have only ice, water, and vapor. Right? But there are some more forms of ice, which if somebody is interested, you can definitely go through. But what's most important to start with is to have a knowledge of something that defines the state of the system. For example, pressure, temperature, volume, number of moles, right? These are the kind of things that you really need to know if you wish to define the state of the system. Okay. Yeah. Just a couple of more definitions and then we start. There's some of these variables which you need to define. For example, pressure, temperature, right? These fall into the category of intensive variables. Intensive variables, all it means is that they do not depend on the amount of the system. When you say n number of moles, what it means is amount of the system at hand. Right? N defines the amount. Then there are other things which actually depend on amount. For example, volume, right? Well, those would fall into a category of extensive variables. You can intensifies an extensive variable, right? You could actually divide V by the number of moles and get a molar volume, Vm or V bar. These are, either of these is used in the books. So this does not depend on the amount of the system. The molar volumes is a constant for a given system, right? We'll come to the equations of state and then we'll understand what I mean. That it's constant. It does not depend on the number of moles. Yeah, as long as I don't change temperature, pressure, all that is understood even without mentioning, right? Okay. So the common notation that we're going to follow is all kind of repetition for you guys, and that's why some of you look very, very disinterested, but anyway, let's to write the number of moles. For example, I have 2 moles of hydrogen gas at 1 bar 100 degrees C. Okay. So the notation is generally 2 moles of hydrogen. We define the state of the system. It's gas. It's at 1 bar. It's at 100 degrees C. Okay. If I wish, I could have chosen some other units, right? But bar is the SI unit. Here I could have chosen Kelvin. We'll come to the Kelvin scale in a moment. Okay. But what you should remember is that, for example, there's something called the standard. This is some definition, so that these definitions never change the signs, but it's something that you have to get accustomed to in order to understand what's out there. Standard ambient temperature and pressure. Okay, so the standard ambient temperature and pressure is defined as 273.15 Kelvin, 1 bar. Okay, this is abbreviated as SATP. The older version, that's known as STP, which is standard temperature and pressure, which is 0 degrees C, 1 atmosphere. Okay. The molar volume of an ideal gas at standard ambient temperature and pressure, which is a newer standard, is actually, let's use another color over here. Does this show blue? Yes? 24.789 decimeter cube per mole. This one is 22.414. So the old standard is the one that we've mostly seen, right? 22.414. That's 24.71789. Things which according to me need not be remembered, right? Okay. Apart from these definitions, let me see if I still have more definitions. Bear with me a bit more for a while, and I'll be done with these. Okay. The last thing is we're going to talk of transformations. Right. If we are talking of energy changes, of course we are going to talk of something going from one state to another state. And in most cases, what is important is how it goes from one place to the other place. That is the path. Right. And I'll not bother about it now, but normally what you will do is you would draw a pressure versus volume diagram, for example, and say what part, it's the initial point over here, I, to the final point over there, F. You could go this way, you could go that way, you could go like this and this, right? All various paths are possible. You'll often hear the terms reversible paths, irreversible paths, isotherms, adiabats. Okay, I'll define these things as and when we come across the examples, right? Isobaric, isochoric, right? So, and then there would be another thing over here, would be that some of the properties actually depend on which path I take, but some of the properties depend only on the initial and the final. What are these called? Huh? Everybody says I can do. Right. So state functions and path functions, and we'll develop the formalism of the state function and path functions, how to calculate them, how to actually determine them. Right. I hope I'm done with the definitions. And yes. So, we can then straight away go to the zeroth law. Now, what the zeroth law says is that if we have three containers, well, what I normally do, I should do it again. I end the topic and ask you if you have any questions. So I ended some definitions, which of course everybody knows I completely understand, but for the sake of completeness, I should tell you some things, right? So let's say we have three containers, one box A, one box B, and a third box C, right? And I connect them. So all these three are, right, they're all in thermal contact. Whatever time it takes doesn't matter, but these will finally come to an equilibrium. If A and B are in thermal equilibrium with each other, what it means thermal equilibrium is whatever the amount of heat that flows from A to B, the same amount of heat flows back from B to A. Okay. In fact, remember, whenever we talk of equilibrium, it's not that things stop flowing. Even when you talk of chemical equilibrium, things are always dynamic. Things are happening. They haven't stopped. It's only that whatever happens from this to this end, the same amount of events happen from that end to this end. So it's always a thermal equilibrium. If that is the case, and then I have brought another body C over here, and if C is in thermal equilibrium with B, it will also be in thermal equilibrium with A. Right? That's the zeroth law. Fairly common sense. Right? Something which we have experienced every day. We put some ice in water, water gets cold. Right? Even the container gets cold. So things which we have, actually thermodynamics is something which you have experienced which you experience every day. Quantum mechanics, on the other hand, is not so intuitive. It's more new for you. So what you do is, you say, okay, if actually I could measure some property of C, which depends on temperature, which depends on how much amount of heat is there, I could actually develop a temperature scale or a thermometer, right? So the zeroth law gives us the concept of a thermometer. For the thermometer, what do you need? You need some function, some property that changes with temperature, right? So the first thing that you need is a function which changes with temperature. I am deliberately writing small t for temperature. Okay. So what else do I need? I need some reference points, right? I need to define the scale, right? So I need some reference points. Do I need something else? Okay. Rather than being abstract, let me plot it over here. That's my temperature. That's the function, which is a function of the temperature, right? And I have reference points. Normally, what are the reference points that are taken? Triple point will come to later. Just give me another 5 minutes. I'll come to that. So, I mean, we are talking of the 1800s, fine. What if I give you, okay, please calibrate a thermometer. What would you do? Right. That's the easiest thing to do. So I'll take two of those. One is the melting. So I'll put it in ice. Ice. I won't put it in ice. Remember that. It's ice water mixture that you have to put it in. Ice can be at a much lower temperature. Remember this. A lot of people make this common error. Ice at 0 degrees C. No. There's an ice water mixture that is 0 degrees C. So, let's say this is a temperature scale and we've determined I need some. So here we have one data point over here. Whatever that function is has this value at the melting temperature of ice, of water, the melting temperature of water. And the other easy thing to do is to boil it, right? Which I know, of course, by common sense that it's got to be a higher temperature, so I'll make that point somewhere over there. So I have two data points over here, but I still don't have a complete scale. Okay. I want to make a complete scale out of it. What do I do? Just make a straight line, right? Forgive me for my straightness. Oh, better than what I expect. Make a straight line over there, right? And now, whatever this value of the function is, I can read off the temperature. And that function could be simply the volume of a liquid. For example, when you use mercury thermometers, what you use is, or alcohol thermometers, what you use is volume of alcohol or mercury. It could be the resistance. That's what you use in some of those electrical thermometers, right? That's where I wanted somebody to object me and put the third point as interpolation scheme. Great. I just assume things are linear. They may not be. How can I be so certain that at 0 degrees C, mercury will have this volume, at 100 it will have this volume, but at 50 it will have exactly half the volume? Why? It could be quadratic, it could be some random function. Well, normally physical properties don't have such random functions, but it could be quadratic, it could be cubic, it could be anything, right? So it's very important to decide on the interpolation scheme. Right? Right. When you're talking of electronic thermometers, you're using diodes, which do not have such linear regimes everywhere. So you have either only a certain regime where you can measure it, or if you want to go further, you have to not use an interpolation scheme that's linear. Good. What else? Do we need to worry about anything else? Or are we ready with our thermometer? You've got the function, you've got reference points, you've got the interpolation scheme. Upper and lower would just depend on the material. We need a material, right? So the material properties would determine the upper and lower. Well, actually, the fourth one should have come the first, right? First, I need a material. Okay. So that tells me that I can actually have a temperature scale if I have these few things at hand. What people did was actually, in earlier days, people used to measure temperatures. One of the first few scales which I heard of is the Romer scale. So that guy was a Danish, and he put 7.5 degrees Romer for the freezing point of water, because in Denmark, the temperature then would never go below zero. People were somehow scared of negative temperatures. They didn't want that. The Fahrenheit scale is based on the Romer scale with some multiplicative factor of the Romer scale. Okay. The centigrade scale is more on the decimal system. 0 degrees centigrades for, so this is the one that's 0 degrees C, right? That's the melting point of water, and this fellow is nothing but 100 degrees C, which is the boiling point of water, and then it's actually marked at equal gradations. That is a linear interval, assuming that mercury in this particular regime, mercury expands linearly. We'll come back. What's very interesting in this scale is something that you see over here. I've just interpolated, I've not done anything else. But this guy is cutting this particular function at 0. And one of these functions is very interesting. That brings us back to Boyles Law. If I put that function if I put this function as what's Boyles Law? Limit pressure approaching 0 P times B is a constant. That's Boyles Law, right? And let's use this is at a particular temperature. Remember, the temperature is held constant. So if you want, we can put it like this. Now, my function f of t could be this fellow, limit of pressure approaching 0 P times V at a constant. Okay. Now if I use some gas which is obeying the Boyles Law. Remember, some gas that is obeying the Boyles Law is definitely an ideal gas. Which means, no, since nothing is ideal, as I said, which means it has to be an inert gas. With all likelihood, the experiments have been done with an inert gas, and at very low pressures, right? And temperatures are high enough. We're not close to 0 Kelvin. So of course, it's more like an inert gas. It's very close to an ideal gas. Okay. So it behaves almost like an ideal gas. So we use this particular gas and see what this property comes out to be. Again, on the same scale over here, I have limit of PV at P approaching 0 and the temperature T over here, right? And at 0 degrees centigrade, I have some data point over here. At another temperature, whatever you want to take, I have another data point over here, and then I connect these two data points linearly. Right. Since I know, according to Boyles Law, that this should be linear, right? No, according to Boyles Law doesn't tell me anything about temperature. It's the Charles Law which tells me that it should be linear. Okay, and there it cuts the x-axis and makes this function 0. Right. Pressure is 0, volume is tending to infinity. Right. If this function is 0, that means both pressure and volume necessarily have to be 0. Yes? So if the volume is 0, I don't have any gas. This particular temperature is minus 273.15 degrees, this one.
So you said as pressure is tending to 0, volume should be infinite.
No.
Volume should be tending
Just general feelings. What do you think? If pressure is tending to 0, volume tends to, right? It does. But if I want that function to be 0, that means both of them should be 0. So remember, again, these are all very ideal things. A real gas will not exist at this temperature. Right? From whatever you studied earlier, you know that everything condenses before it reaches 0 Kelvin. Okay. Anyway, so this particular thing, minus 273.15 degrees centigrade, gives you a natural scale. Okay. A natural scale of temperature, which I now denote as 0 of temperature. Okay. So if I do that, right, this scale becomes T plus 270. Sorry. T minus 273.15, whatever I want to call it, right? I have my temperature still in degrees C. So let me then write it in the format temperature in degrees C minus 273.15. That's a new scale which we call which we denote as temperature with a capital T, and its units are the Kelvin. What you don't use is, there's some semantics over there, nothing more, but you don't use the degree sign when you write Kelvin. Right? So this is, but you do speak it. Huh? Thanks. I wrote plus, but I don't know why I changed it to minus. Right. So, what you have is, right, you don't speak, you don't write the degree sign, but you do speak it. So what you write over here is 0 Kelvin, looks more like okay, and sorry, this is the point where we were, right, in the earlier graph, that point up there, right? And then we need a second reference point, right? Earlier we had two reference points, one was the melting, one was boiling, but now we have something which is very sacrosanct, zero Kelvin, right? A gas cannot go below this temperature. An ideal gas cannot go below this temperature. So what is it? Is there something else which I can have? Something which does not change. And that's the triple point of water, for example. So if I take the triple point of water, that is fixed, right? When we study about the phase rule and the phase diagram, then you will realize that the triple point has 0 degrees of freedom, something which I am telling you even before you learn. Which means nothing can be changed in that. The pressure is defined, the temperature is defined, right? You cannot change it at all. So if I have something fixed like that, I could take that particular point, the temperature triple point, which is actually 273.16 Kelvin, and 10 to the power minus 3 bar, 6.1 into 10 to the power minus 3 bar. It's a very low it's a very low pressure. And the triple point is when all the three states of matter, solid, liquid and vapor, they coexist at that particular temperature and pressure. Okay, it's not just the temperature. And that's why it's invariant. Yeah. If you remember the phase diagram of water, those three lines like that. That dot over there. On the y-axis you have pressure, on the x-axis you have temperature. That dot over there, it's only one dot, defined by a particular temperature and a particular pressure. You can't change it. So you've got two reference points which nobody can change. Very natural, right? One is a 0 Kelvin. You can't change it. It's a natural thing. The other one is the triple point of water. And we've chosen to be water. It could be anything, right? You can't change that either. So you have two temperature points which cannot be changed at all, right? Because when we talk of melting or boiling or anything of that sort, you know that as the pressure decreases, as you go towards the mountains, the boiling point decreases, right? So you could have different scales then. But here, something is fixed. And now if I interpolate between these 2 points, sorry, this 0 Kelvin and the triple point, then I get a linear scale. I cannot go below 0 Kelvin. It doesn't make any sense. And here we have, so that's the ideal gas temperature scale, right? That's the ideal gas scale. Okay. Right? What's the slope of this line, what we have over here, or the scale that we have over here? That should label always limit PV. Right? What is the slope? Huh? Yeah, exactly. The slope essentially is limit of PV at let's just write the triple point minus the limit of pressure times volume at 0 Kelvin, which is 0, divided by 273.16 minus 0. Right. That's the slope, and that slope is a constant. Right? That's my function. That's what I started with. That's my function. See the see the y-axis. What I'm plotting is always one particular function, limit of t times v as p approaches 0. Remember, I had to think of one property over there. One property. This property could have been resistance, volume. What I chose was p times volume as p approaches 0, which essentially is nothing but it's constant according to Boyles Law for a given temperature. So this particular constant is nothing but the ideal gas constant R. Yes. And what was this? If I write the function on the y-axis is nothing but mx plus c. C I know is 0 because at 0 Kelvin the function is going to 0. So if I write limit of p approaching 0 p times v, that's the function that that's the property that I'm measuring, is equal to the slope times the temperature T is equal to, this slope is the constant R, right, times temperature T. If you want, we can put R, we can put this N over here, right? Or we could have used the molar volume. Either ways is fine. So if I see the left side and the right side, what I have is essentially P times V is equal to nRT. Yes. That's your ideal gas law. Yes. That's the ideal gas equation. Now, what I have done is something very subtle. I have just removed this limit P approaching 0. Yes? I have written your more familiar form of the ideal gas equation. But this is how it has been derived. Yes? So what you always have to remember, always, is that the ideal gas equation is a valid approximation only when your pressures are very low. Yes. There are other things also which we could have derived. The ideal gas equation is valid only when the temperatures are high, right? Why? Because when the pressures are low, the molecules are far apart, they don't feel the presence of each other. When the temperatures are high, the mean speeds are high, right? So the attraction forces cannot pull. So if I'm running very fast, yes, somebody can't pull me easily. You can't stop somebody who's going very fast. But if you're slow, then you can be stopped more easily. Whatever the attraction these molecules have, if one molecule is running away very fast, that feels less attraction from the other. But if it's going very slow, and then there's another molecule that is sitting over here, and it gets attracted to this one more easily. So that's why high temperatures, low pressures, these are the common things which you already know that are needed for the ideal gas. This is exactly where it comes from, and very cleverly we just remove this limit, and in a number of instances we forget that this limit exists, and then we get into technical difficulties with this equation. Okay. So if you get into such difficulties, always fall back on the fact that one, this is an approximation. Right. Mathematically, people come down to 0 Kelvin and then say, oh, look, this can't be possible. Of course, it can't be possible. There are a lot of things you'll come across, and you'll say, sir, this can't be possible. Sure, it can't be possible because this doesn't represent reality. What it represents is under certain circumstances, it can approximate the behavior of the gas. That's all. We're just trying to make our own life simpler by using easier maths. Okay. But otherwise, you can go to other equations. So this is one of the equation of state. Right. This links. These are the few things that I need to know. I need to know the number of moles. I need to know the temperature. I need to know the volume. Pressure, I get out of this. Or either way, right? I can get volume out of this if I know the other three. So I need to know something. Let's usually what we use is pressure. Let's say, okay, pressure is a function of N V T. I could have written volume is a function of P N T, or temperature is a function of N V P. Doesn't matter. Right? You normally write it like this. It's the way things have been developed. It's the way we find more easier because all the literature goes like that, right? Now, this is called an equation of state, something that relates various variables to each other, right? An equation of state. Let's try to be more realistic then in these equations of state. I have told you that PV is equal to nRT is an idealized version, right? So how about trying to slowly get to the real forms, right? I know if P Vm is equal to, so this is just molar volumes, right? If P Vm is equal to RT, then if I define something like this, P of Vm by RT is equal to Z, Z is always going to be equal to 1 in the ideal case. What I could also do, yeah, we are dealing with real gases, right? And there's no guarantee that Z has to be equal to 1, right? It could be greater than 1, it could be less than 1. Under what circumstances would it be greater than 1? And under what circumstances would Z be less than 1? Right. So let's write this equation slightly differently. PVM is equal to RTZ. Okay. And let me say that this Vm is the real one. So this is Vm, and let me write this, the real Vm. And let me divide this equation on both sides by ideal. I am dividing by the same thing on left and right, yes? Because in the case when I am talking of ideal behavior, then PV is equal to RT. So I am just dividing by the same thing. So what I am left with then is simply this fellow, Vm real divided by Vm ideal is equal to Z. Now, if Z is greater than 1, then the molar volume of the real gas is larger than the molar volume of the ideal gas, which means my molecules are flying apart, they are repelling. Yes. So what we have over here is no, we want some more colors, huh? Repulsions dominate if Z is greater than 1, yes? Yeah, only if the molecules were repelling each other, they would have flown apart, right? And then only in that case, the molar volume of the real gas would be larger than the molar volume of the ideal gas. That would make Z greater than 1. If Z is less than 1, then actually the volume of the gas has compressed. That means the attractions dominate. So there are attractive forces over here. We have attractions here. Right? So essentially, if you look at this, this is nothing but, I could define, or in English I could say that this is how much the gas has compressed or expanded. Right? This is the ratio of the actual volume upon the ideal volume. So how much the gas has compressed or expanded, that's what. And that's why this fellow Z over here is called the compressibility or compressibility factor. So this is the first step towards introducing a non-ideal behavior or a real behavior, right? So next time we'll have a look at some of the more real gas equations of state.